Hey everyone, Michael Unger here with another edition of Ask an Astronomer, as always with our trusted astronomer who's just a couple doors down from me on unceded territory of Musqueam, Squamish, and Tsleil-Waututh, and that is our science fiction nerd, Marley Leacock. Hey Marley, how's it going?
It's good. I science fiction. I think I like specific science fiction. I'm not a all science fiction nerd.
Okay, so very specific, but that is the topic of today. So if you're out there watching, want to get into this conversation on YouTube, on Facebook, ask a question. You can ask any question out of the universe, even if it doesn't even pertain to science fiction if you want. We'll get into that. But last episode, 2 weeks ago, we talked all about the Dune world. Now, in lots of different kinds of science fiction, especially when it comes to space, I find it interesting because we get to visualize other solar systems. And of course, back in Star Wars land, that gets visualized with completely fictional solar systems. And in that sense, you get lots of creativity, in different kinds of worlds, different kinds of stars. So that's going to be kind of like how in this episode, we're going to take a look at some of these fictional solar systems and maybe some of the real exoplanet solar systems that we found, right, Marley?
Yeah, more or less. I kind of went the star route more than anything because I just the whole idea is very cool and there's a lot of fun animations I could show. So that is
All
that
right.
is the idea.
Well, let's get into it.
All right. So first, though, Michael wanted me to throw in a little bit about that fun event that happens. This happens every time. I never know if it's supposed to happen at the end or at the beginning. That happened over this most recent weekend.
Yes.
Yes,
Where were
yes.
you for the celestial event of the year?
I was in Seattle, which I was a little bit worried that I wouldn't be able to see it, but I was able to, which was pretty cool. Didn't think I'd ever get to see them like come that far down, that far south at all. But if you missed it, like if you were like Michael and in cloudy zone and not able to see it, there
Well,
was
let's just say that I was actually in probably a very good location
mhm.
normally. I was in Lethbridge for the CanSat competition, and we actually drove to an actual dark sky observatory, all set to watch them, but it clouded over. So, but I saw a little bit. I definitely saw some colors, and what was interesting is that when I put my camera up and opened up the aperture, the camera was actually able to show the colors a lot more than I could just with my own eyes.
Oh yeah, cameras are our eye. Yeah, cameras are a lot better than our eyes are. Cameras don't have to blink. We have to blink all the time, and every time we blink, that kind of messes up our ability to view, especially because the aurora aren't stationary, right? They move and they're very dynamic, and so us blinking, our eyes have to reset every single time. Whereas the camera can just stay open for however long you set it for, and it's able to collect that light and view it. I had the same thing. When I looked at the sky with just my eyes, it looked very muted, but once I used my phone, the colors really started to pop. So, what caused that? Like, this was a huge storm, severe and extreme geomagnetic storm, likely on May 12th. So, that was due to several coronal mass ejections coming off of the sun. So, a coronal mass ejection is when actual physical parts of the sun and their associated magnetic fields erupt off of the sun, travel through space. And they're only really a problem if they hit us, which in this case, several of them did. Several of them ended up, on trajectory with Earth and ended up hitting us here. What's interesting, though, is I looked at the timing of like when the alert went out and when we could expect the arrival at Earth. And they put the update out on May 11th at 1:30 p.m. Eastern Daylight Time. Was so, 3 hours earlier Pacific time. But the actual event was supposed to happen midday, like arrive at Earth midday, May 12th, UTC, which would be about May 12th at 5 a.m. So they gave us, pretty decent amount of warning that this was going to happen, which was good because a G5 severe storm, and a G4 severe and a G5 extreme geomagnetic storm that can affect radio communications, and is particularly damaging to satellites. So it's good to have enough time, not just to potentially view the aurora, but also for people where it matters to prep their equipment to do what they need to do for that. So I was interested about the timing because it's not always, it depends how fast they're moving. CMEs can move between 250 kilometers per second to 3,000 kilometers per second. So
Hmm.
your timing can get changed up there. And this is what is responsible for what happened. The sun is currently in its active cycle. So the sun, has a period of activity, and we are quickly approaching solar maximum, which is when it reaches its peak in activity. Then it dips down. We reach solar minimum. It's pretty quiet, and then we ramp back up to solar maximum. A whole cycle takes about 11 years. So we're, reaching about halfway through one of these cycles, and we have two photos here. The image on the right is of the sun's photosphere, which you can think of as like the sun's surface. And the image on the left is the sun's corona, which is like the sun's outer atmosphere. The coronal mass ejections originated and are associated with flare activity from region 3664. And I'll give you one guess as to what region 3664 is. It's this really, really busy region over here. So that is a collection of several sunspots, which are how we mark activity on the sun. So when the sun is more active, its surface will have more sunspots than when it's in a low or quiet activity zone. So there is a lot of activity going on here, a lot of prominences, which you can kind of see in the corona image, right? We have lots of material. We have some prominences happening above as well and on the other side, but a lot of energy kind of all tangled up in this area. And this is where those CMEs originated. Pieces of the sun were ejected from this area, bunched up together, and hit Earth, which was I ended up with some pretty spectacular views. And there's also a video I can show of what it actually looked like for a spacecraft. So while we were safe, because our atmosphere is what protects us, our magnetosphere and our atmosphere, these particles are charged, they have a magnetic field. And so when they interact with Earth's magnetic field, they get funneled right to the north and to the south poles. Spacecraft don't have that protection. And so they get bombarded with a lot of radiation and energy. If this video wants to sort itself out, which it might not actually, which is too bad.
There it goes.
There it
That's
goes. Right. But the day needs to be right. So it happened on the 11th when it actually went out. There it goes. Let's rewind. So it's not that one. It's that one. That was part of the part of the CME coming off of the sun. This is now May 12th moving into, and so it starts to settle down. Oh, sound. It starts to settle itself down. But that big spewing of material is what they saw. And you can watch as the solar wind picks up all of these particles in the spacecraft's field of view. This is SOHO by the European Space Agency. It gets bombarded with quite a lot of material and particles. And that's part of the early warning detection, right? Spacecraft will feel it first. That information gets sent to us here on Earth and gives us an idea of what to expect and when to expect it coming. So it was a really cool event, really remarkable event. Looks like NOAA had put out a warning that maybe we could expect something this weekend or this week. Doesn't look like it. Their next 3 days are pretty quiet. So, but stay tuned because the sun does what it wants. So especially if everything's moving on the surface, right? The sun rotates. If these come back, maybe something else.
And just to give us a sense of scale, because I think one of the things about these 2D images, when we see the sun and we're looking at these different planets, it's just the sheer scale. Because those sunspots, like in relation to, say, like the size of the Earth, how big are these sunspots? Or I guess how big are these flares, right?
Yeah, it's a good question. I didn't look up scale because it's coming off of the sun. They're quite massive. But I can look up how the size of region 3664 on the sun. It's still producing flares. That's good. But I'm not sure if there's ever a good way to explain the size of things when it comes to the sun in comparison to Earth. It's big.
Yeah. I guess the point is that these emissions that are coming off of the sun are incredibly massive.
Yes. Right? So sunspots are typically the size of Earth, right? Usually that's kind of a rough estimate for them. As of May 10th, the sunspot region that was responsible for the CMEs grew to be 15 times wider than the Earth. Okay. So the sunspots themselves were quite large. The ejections themselves, those sizes I think are less easy to think about because as it moves, it diffuses, right?
Yeah.
So its size opens up, it becomes less dense, which is good, but that makes the physical size it's taking up, like the physical space it takes up, much larger. But yeah, I guess this little region was about 15 times as wide as Earth. So
Hmm.
pretty big region of a bunch of sunspots in that one spot.
The other thing that I was curious about, and it actually came up during the CanSat competition, was these mini little satellites that we released out of a rocket at 1,000 feet. A lot of them had GPS, and even though we weren't experiencing the aurora, which is what we normally would be associating these sunflares with, but we are still being hit during the daytime when this is happening. So would the GPS would it affect that at all? Because there was a lot of like GPS issues during our launch day, and so a lot of the kids were wondering, potentially if some of this activity might have been affecting it.
Oh yeah, it can. So like geomagnetic storms will mess with GPS satellites, especially if it's a strong enough storm. And because we were at, such a severe, like the highest warning. So solar geomagnetic storms are ranked on a scale from 1 to 5. And you can think about them similar to like, well, I guess for Vancouver, like earthquake scales. And so 5 is like the highest ranking you can get. And so when it's that high, it will impact like high frequency and low frequency radio communications, which, GPS is based off of radio communications.
Right.
And it will impact the satellites. And part of the problems is that it can either, overload them and shut them down, or it can also cause them to lose navigation data. So they don't know where their position is, which would be bad for a GPS. That's how that works. So it is possible that it was being affected by the activity in the upper atmosphere from the magnetic storm.
Okay, awesome. So if you're out there watching and want to get in on that conversation around the Aurora Borealis, if you saw them, put them into the chat. Let us know where you saw them and what you saw, and maybe what you saw with your camera as well. But let's transition now to our main topic of the show, and that is to a little bit of science and science fiction. Now, Marley, as you know, I am a true diehard Star Wars fan. I saw Return of the Jedi in the theater, but one
Nice.
particular scene that has always stuck with me is from the original Star Wars, where Luke walks out and he's sulking. He's being a typical teenager that doesn't get to go and play with his friends. And there's the classic John Williams score swelling, and he sees the double sunset, which at the time was pure science fiction. But you're about to tell us, Marley, that this is not science fiction anymore.
No, it is actually way more common than we thought. So the binary sunset, great track. Shout out John Williams. And also the part in this film, right, when Luke sees the two suns setting on Tatooine, is actually way more common than we anticipated. Most stars actually have a partner or a binary pair.
Mhm.
That's pretty common. What becomes less common is finding planets that are able to survive being in orbit around two stars that are
Okay.
also orbiting each other, because gravity starts to get really messy. If you're into physics, oh, this doesn't want to play. That makes me so sad. It's called the three body problem, right? So you can have three bodies all moving. In this case, it'd be two stars and a planet. And different changes in gravity and different changes in motion will impact the orbits of these bodies, right? So you need very specific conditions for a planet to be able to coexist with two or more stars, right? It's a lot of math. It's very frustrating. Luckily with computers, we're now able to make these beautiful animations that show us of different things, but doing it all by hand is gross. The more stars that you add, the more unlikely it becomes that a planet will be able to survive those conditions. So, one star, one planet, pretty good. Two stars, one planet, we're getting risky. Three, four, 5 stars and a planet, that planet probably getting ejected. Because the other
Mhm.
thing you have to consider is the mass of the objects. The more mass you have, the more gravity you have, the more, weight you have to throw around, you could say, right? So the more those perturbations can happen, the stronger those changes, the more likely it is that the smaller object will just get tossed out of the system entirely. But that's not to say that we don't see it. We actually do find planets that are able to orbit around two stars or binary stellar systems. They're called circum something planets. I can't remember now. Kepler 16b was one of the first ones that was like confirmed to be around two active stars. As is always the case in astronomy, there's another first detection of one of these planets, but it was a circumbinary planet, I think is it. But it was orbiting a star and then a brown dwarf. And so it was like, does that even really count? Because what are brown dwarfs anyway? It was the whole thing. But this one is orbiting like two stars, you know? Like, yeah. 245 light years from Earth, a K type and an M type star. So one that's close-ish to our sun, and then an M type star, an M dwarf star. Those are very, very small, very, very dim, very, very cool type stars. The system itself is called Kepler 16, found with the Kepler Space Telescope using the transit method. So we had already found this binary stellar system, but using the transit method, we were able to detect the appearance of a planet because it was adding to the light curve that scientists were seeing. The planet Kepler 16b is a giant planet, mostly composed of gas. It's like a gas rocky split, they think, based on its mass, about a third that of Jupiter's. And you can't see any of this unaided from Earth. You do need a pretty powerful telescope if you wanted to be able to view it. This is the light curve of the system, or an adapted version of the light curve of the system. So we have the transits of the stars, right? So there's two different eclipses going on. So one star is much larger. Kepler star A is that K-type large star. Star B is that, very small M dwarf star. So you have these dips, more of a dip when, B is occulted versus when A is, right? You have these two different dips happening, a primary eclipse and a secondary eclipse. And then you have these also really, really tiny dips that are you're almost unable to see. And they also don't happen at the same time every single time, right? They're not as common. Those tertiary and quaternary is what they're called eclipses are at quaternary, I think. Yeah, like third and fourth eclipses is when the planet is transiting each one of those stars. So you actually get four different transits. You get when star A passes in front of star B, you get when star B passes in front of star A, and you get when the planet goes eclipses star A and when the planet eclipses star B. So you'll get four different dips in your data. This was very hard to parse out, but they did find it out and were able to determine that there is a planet that would have a double sunrise sunset, right, as it orbited around these two stars. But there's more, because these systems, you can just keep going and they get weirder and weirder and weirder. So this system is called HD 133131 or HIP 73678, which is about 163 light years from Earth. And these are what they call stellar twins with their own families, right? So these two stars are only 350 astronomical units away from each other. So 350 times the distance of Earth from the sun. Which is really close for a binary pair of stars. That's very, very close. They're also the same spectral type as the sun. So they're pretty much the same star. And they're very, very close to each other. And these stars are orbiting each other, or they're orbiting, their center of mass, the barycenter of the orbit. And they eclipse each other every 4,240 years, which, takes a while. Yeah. But each star has their own planet. So the planets don't orbit around each star. Each planet orbits around its own star, and the stars orbit around each other. So you get a lot of interesting systems. Right. So star A has two planets, planet B and planet C, whereas star B just has one other planet, planet lowercase b. It's interesting because now you've got all these different things moving, but they're all stable within their own systems, and they happen to also be orbiting each other.
Nice.
This last one doesn't involve any planets, because if you remember, the more stars you add, the less likely it is for planets to be able to remain stable. This is a structure of a sextuplet system. So
Oh
there's
boy.
6 stars all in binaries with each other. So we'll go through it, stage by stage.
It's like one of those like reality shows, like John and Kate plus eight, like you got 6 stars here.
uh,
Can a planet be stable? Tune in.
Tune in. This one, I think, in the description that NASA gave, it was described as having gravity similar to that of a Rube Goldberg machine. Like everything's just really intricately working out. Which, yeah, is accurate. So we have a system, or system A. This is made up of 2 stars, right? Then you have system B, which is also made up of 2 stars, and system C, which also is made up of a binary. So you have, 6 different stars. You have 3 binary pairs. System A and System C orbit each other every 4 years. So now we have a system, System A, System C, and together they make System AC, because while these stars in System A orbit each other 1.3 days, the stars in System C also orbit each other 1.3 or 1.6 days. These two systems together orbit each other every 4 years. So these 4 stars are moving around the center of mass once every 4 years. But then that one system orbits around the B system once every 2,000 years. So you got 4 stars kind of as one system rotating around a center of mass with the B system on its own. So you've got a lot going on. This system is 1,900 light years away. It's very, very, very far. And it was discovered by the TESS satellite. I don't believe any planets have been found with this one. Hard to know where they would go. Probably, if anything, around B, because it's much further away.
Yeah.
I feel like this would be really messy. The AC system would get really messy really fast if you were a planet.
So I guess, one other question that comes up in my head as you're showing me this, and as you're saying that these systems are quite common, however, they may not be as common to find planets in these systems. So rogue planets is another something that we've been talking about. They're hard to find, obviously, because they're not giving off any light. But would that lend to the theory that there are much more rogue planets in our galaxy because we have found these systems that would obviously fling out these planets pretty easily if they were anywhere close to them?
Yeah, no, those two ideas like work really well together, right? If any of these tried or had a planet and then entered into a binary and the planet got ejected, that would become a rogue planet. In fact, this Kepler 16b, I think it was, the planet itself, I might be mixing it with another Kepler system, but I think it was this one. They don't think that this planet originated in this system, in this plane, is that something moved it to where it is today, whether it was a rogue planet or there were other planets. There were other planets that then, have left and this one's left behind. I don't know. But a lot of these, it seems like how the planet start there is also part of the mystery, because there's so much going on. How in our models of planetary formation with disks, how does a disk form properly enough with all 6 stars moving around? That's also part of the question.
Okay.
The last one are Xray binaries, which are just fun. This is an artist's impression of a high mass Xray binary, which you're seeing is an exchange of material between a stellar remnant and a star, but it could also happen between 2 stars themselves. So the larger, more quickly evolving star can run out of nuclear fuel, will run out of fuel to keep itself burning, explode in a supernova, and leave behind a far denser white dwarf, neutron star, or black hole. Right. So what's happened is in our binary pair, the more massive star has died first and has left behind a stellar remnant. The more powerful gravity of that collapsed star will start to accrete material from the binary companion if they're close enough. If they orbit close enough together, the leftover stellar remnant will have enough gravity to pull away material from the companion. That produces X-rays as the material is falling onto the collapsed stellar remnant, and it gets heated to more than 1,000,000 degrees Celsius. And that amount of heat corresponds to enough energy to be able to show X-rays. So they are very, very X-ray bright. And these, if it's a white dwarf or a neutron star, I think white dwarf is more common though. Once it reaches a certain amount of mass accumulated, it will go nova. So it will actually explode into supernova. And I think very recently there was one discovered, an X-ray binary discovered that they anticipate might go supernova in some time, but it was in preprint. It hasn't been formally published yet. So I don't want to put the paper out there just yet, but that's something to be on the lookout. These are also common. This is also how we find black holes as
Oh.
well, is because they accrete material. We can't see the black hole itself, but we can see the accretion of the material and work out, okay, the star is losing mass. What would the gravity have to be? Oh, okay, that's the gravity. How massive would something have to be? Okay, stars don't get that big. It's a black hole, right? So it's a method we can use to find black holes as well.
Okay, so lots of different options here for binary solar systems. We see them occasionally in science fiction. You know, Star Trek, obviously, actually, this comes up a lot more often, going to a lot of different variety of solar systems in the many iterations of Star Trek. If you know of some out there that are of interest to you, we're always wanting to learn more. You know, one of the things, obviously, from the original example from Tatooine, I think it was probably just a very basic idea that if there was two stars, it would make it doubly hot, which is why Tatooine is a desert world. But perhaps, as you can see here, maybe one of them is a red dwarf, so maybe there's more radiation coming off. That wouldn't be great for life, but Tatooine is also kind of like a bit of a strange world in its own right. Is there anything to be said just in terms of Tatooine as a world being how it is, and is it still science fiction to think of it as a world that we could actually see in our own galaxy?
I don't think it's too far-fetched science fiction. The ones that I mentioned today, like the Kepler 16b, that one is technically in the habitable zone of its system. It sits about as far out as Venus does from our own sun. But the problem with Kepler 16b is that it's a gas, mostly gas, right? There's no solid surface for us to walk on. And that is not to say that there aren't planet like stellar systems like this that host rocky planets. What that says is that our methods for exoplanet detection favor large gas giants, right?
Yeah.
Because we look at the amount of light that dips, rocky planets tend to be much smaller. So I don't think it's necessarily impossible. I think, would it be habitable for life? Probably not the best bet, because you're being blasted by twice the amount of radiation. You'd have to have a pretty strong atmosphere, pretty strong magnetosphere, something protecting you from that. Imagine the aurora you would get from two. Anyway, like, so maybe not, but I don't think it's as unlikely as we think, I think is my answer. I think there's probably a system out there with two stars with a planet orbiting it that's rocky and is probably barren, the same way Tatooine is.
Well, and Phantom Menace was just re-released in the theaters recently, and if you remember that classic poster when the movie came out, which was young Anakin, and he was casting a shadow, and the shadow
Mm-hmm.
was Darth Vader. Although they could have been creative there and had two shadows,
Yes, they could have.
that would have been quite very interesting. But love thinking about these ideas. Of course, we've got one more episode. I'm not going to be here for the next Ask an Astronomer, which is going to be in 2 weeks on May the 30th, but we'll have a special guest with you, Marley. And of course, if you have some ideas, send them to us. Send your questions into info@spacecenter.ca, or perhaps a science fiction world that you'd like to know a little bit more science behind. You can also go to our Facebook. You can go hit us up through Instagram as well as shout out to everyone that watched this episode, whether on YouTube, on Facebook, on Instagram. Love that you're here. Hope to see all of you very soon. And we have some special events, of course, to check out. We have a very special event on June 13th with Dr. Shandeen Pete. We'll talk a little bit more about that when we come back. I guess I will be back on June 13th. I think that's the next episode that I'll be here. So I will see you all then on June 13th. Take care, everyone.